welcome to Data Science Decoded podcast. Don't remember the number, 30 something. I lost count, and I'm happy to be back. I'm here with Liron and Mike. How are you guys?
All good. How are you?
I'm not bad. I think it is episode number 33, but maybe I'm wrong. I'm pretty sure it's 33.
Yeah, last week, 2 weeks ago, I did with Liron more like a coffee break episode. So I don't know how. You don't count
Turns
this as a
out
paper review.
there's already a podcast called Data Science Coffee Break.
Ah, really?
Yeah, I tried to find our episode and then I found this other podcast.
So it's episode 1. Okay, so it means that we should continue doing coffee break episode.
Is the other podcast worth it?
I haven't watched.
Maybe we should do like cross-pollination.
Yes.
Chat with them.
Maybe we should do something Israeli like Data Science Shachor. Bots, data science bots.
Cool. So to our listeners who cannot see, I'm sharing the screen, and the paper today is Applications of Advances in Nonlinear Sensitivity Analysis, which sounds super general. I'll give some background. So it's by Paul Werbos. I hope I pronounce his name properly. I think it's Polish or something, so maybe it's Werbos or whatever. And this is like more a review paper of his PhD at the time. So this is from 1980. And during his PhD, he worked on mostly about the topic that we call today backpropagation, or the concept of backpropagation in neural networks. So the motivation from our side is to build the background that we need in order to review the papers that come later by Hinton, mostly about what we call today deep learning. And backpropagation is super important.
Daniel, may I add some small remark?
Of course.
Now, this PhD thesis review is 9 pages long. Okay, and each page of this document is quite dense. Let's say it's 2-fold denser than a regular page. So these 18 pages are review of the PhD thesis, and today my PhD thesis was about 100 pages. It was 3 or 4 papers. It was a paper thesis, and if I had asked to write a review, I think it would be close to this 100 pages, but 40, or maybe you told me that he was emeritus, right? He was on pension then when he wrote this review of his PhD.
No. He was born at 47, so he was like 30 something. A few years
so
after.
He was young then. Okay, he was
young.
young.
It's right after his PhD.
But still, I think I tried to formulate it shortly, but it came out very long. It is very short for PhD review. He did a very significant thing, but in terms of length, it is quite short. And today there are many people. They won't mention their names that are doing not very significant work, but they are really, really long. And luckily we have LLMs to summarize. in one sentence.
Yeah.
Convert this to a bullet point.
Yeah.
So I'll give the introduction, or he called it context of the work. I won't read everything, but he says the first part of this paper describes how a small part of the work, the minimum cost calculation of first and second order derivatives of nonlinear systems, makes an essential contribution to the rest. The second part elaborates on another application, a method for stochastic optimization, which becomes feasible only with the help of low-cost derivatives. This method opens up a whole new approach to the field of artificial intelligence and neuron modeling. It is especially efficient with the new generation of parallel computers, which is also interesting that it touches upon some hardware advancements that happened, again, 70s and early 80s. And I'll give a short spoiler to what he writes later, but he says, and he cites Minsky, one of the fathers of AI, a paper we reviewed, Mike. And he also cites early work on neural networks. And he says that in the 60s, they assumed it was binary, all the inputs, outputs, zeros and ones, and they had problems to do derivatives with it. And now, and he cites some new research in his time that shows that neurons maybe are continuous, and then you can model some problems using continuous variables, and then you can differentiate. So that's some kind of a small motivation.
And Daniel, this paper was published after the perceptron paper, which we also reviewed.
Yes. So the perceptron we reviewed by Rosenblatt is from 57, I think, or 55. And back then, yeah, it was, they assumed it was binary. So there was no way to differentiate.
That was actually, it's worth saying that when he talks about neurons here, he's talking to an extent about biological neurons, but he does mention that, and the way they modeled those changed. So initially they thought neurons shoot peaks. You can see a voltage peak in the neuron. And they used to think that, if it shoots, it's 1, if it doesn't shoot, it's 0. And then at some point they realize there is also possibly a continuous variable there, so the rate of shooting is a float, right? How fast does it shoot? So they figure the rate of shooting is the neuron actually communicating a floating value. So that's the paradigm shift he's talking about, if I understand it correctly.
And we're gonna jump into the first example that he starts. And he says is an example of first kind of derivative, he calls it. We're trying to compute. Suppose that we have a nonlinear system with a vector x of n endogenous variables and a vector v of exogenous variables. Okay, so there's like internal and external.
It's worth looking a bit up about the state equation of the system. So it's defining it here. X at t plus 1. It's discrete time. You can say t plus 1. So x at t plus 1 is a function of x at time t and u at time t. So it's a Markov process, right? It all depends on the current state, x at time t. We had the last episode about Markovian processes. And u is anything external that it's like from the outside of the system. So you cannot expect it to be known from the system's own behavior. And this is just the most general form of a nonlinear function. It's just some function of those two is the new state.
And a small remark, f is a vector function. Okay, x is a vector, all the stuff here, vectors and vector functions. And I have a question, f is a constant function. Does f depend on t, or it is the same for all iterations?
No, it's the same, because if it would depend on t, you would have to denote it here. So it would either also be a function of t, or it would be f sub t to denote its dependence of t.
Okay, fair enough. Okay.
Cool. Then he's going to tell us what it's used for. And he says the cost of simulating the model over the whole time range is m times n times t, m and t. And he explains why. And the idea here is focused on sensitivity analysis. So imagine you have the systems and you have inputs and outputs, and I want to change some input a little bit and see how the outcome, the output is affected. Again, it comes from economics and modeling, and I guess they do it a lot. Also, we do it in physical systems, right?
I think he's from energy.
Yeah.
Isn't he from some Institute of Energy up top?
Yeah, there is. I don't know what it is, but yeah. He worked for the government. I don't know exactly if his PhD was related or not, but maybe. And it says, the change in xi of t per change in xj of 1, so if 1 is the input, let's say at time 1 at the beginning of some input I, how it affects after time t the output j. Sorry, input j and output I. Doesn't matter how one affects the other. And he says holding the rest of x at time 1 constant. So that's the idea of sensitivity analysis. And he says it's a fundamental quantity of the system. It goes by many different names. In modeling, it is often called the sensitivity coefficient. In economics, it is traditionally called an impact multiplier. Electrical engineers often call it a transient response. So it's like a delta function. What does it mean by transient? Or like Leon, or it's like the...
It was never called that way when I was in university. This would be the transition operator or the transition matrix, right? So the transition would describe the transition from state 1 to state t.
Okay.
By the way, it is interesting that in economics it is called impact multiplier. Okay, we are talking about derivative here, and I think it can be multiplier if we are looking at all this stuff at the log scale. Okay, because it is not multiplier. Okay, so maybe in economics these equations are.
No, why? If you then forward pass and you look at the sensitivity, so it's multiplier. So you change some variable and you have the effect it does, and then you can multiply them to get to the output.
Why? Why?
It's like the Jacobian, right, or something like that of the system.
Imagine a system, a very simple linear system, right? So the way to go from state 1 to state t would be the transition matrix A to the power of t or t minus 1 steps, right? So it's just, and let's call this new matrix M. So there's a matrix which multiplies x1 and we get x of t.
Okay. Because we are looking at big T time steps. Okay, I was looking at it 1 time step. Okay, just f t plus delta. Okay, I understand. Okay, cool.
Cool. And it says well-known applications which require the use of such first-order derivatives. So second one is mine. First-order derivatives are sensitivity analysis, maximization of a system result. So he says here, i.e. deterministic optimization, so optimization problems, and statistical estimation. In the last two cases, one is actually concerned with the derivatives of a function of x of t or x of some time that is before t, rather than the derivatives of xj at t for any j. But he says it's you can generalize this concept. And also here there's a photo or a figure of what's going on that was not clear reading it. So I don't know if we can explain it to the readers who cannot see it, to the listeners who cannot see it. But the idea here, I'll try to give it shortly. Imagine, again, you have some number of inputs, j, and I number of outputs. So he says you can do like a forward pass or a backward pass. So forward is starting with the inputs, change every one and see how the outcome is affected. And the backward is changing the outputs and see how the inputs are changed. That's as far as I can tell for now. It doesn't really talk yet about the differences.
So from what I understand, the paper talks about backpropagation, differentiation as a way to do sensitivity analysis. And I understand you say that the other common approach at the time was actually perturbing the input. So using a slightly different input and seeing how that changes the output slightly. And then you say, okay, you approximate the derivative that way. That's actually sensitivity analysis as well. But then he's saying one that may not be efficient if you have many inputs to change. But he's also talking about what are you running through? Because if you think about it today, that's kind of related to the way neural networks work, right? So if you think about a convolutional neural network, for example, you have from each representation, from each element in the representation vector, you backpropagate it only to the part that it sees of the image, to the receptive field of that pixel in the representation, right? So he's essentially saying, look, if I do that, I don't have to compute everything. I only have to compute across the receptive field of the different representation levels of the network. So that would be kind of a modern translation of what I understand from the paper. And that makes a lot of sense. And that's why he's saying that it's cheaper to compute. It's not like n squared, where n is the dimension of the vector, so you compute the effect of every input on every output. Saying it's actually cheaper to compute because you have this separation in the way we structure the computations in most simulations.
But look, in the general case, when the number of inputs and outputs is the same, it says the forward cost and the backward cost is the same.
Yeah, well, he says it could be n squared of t. So yeah, he's saying that.
It could be, yeah, when you have more inputs than outputs. That's the idea, and that's what we use today. So today, when we look at all neural networks and we used to do backpropagation, why we do backpropagation? Again, that's what I took from the paper. It's because the output is a lower dimension, right? It's some scalar we're trying to optimize. It's some classification problem.
Well,
and then it's much more efficient to do backpropagation.
Well, you're correct in the sense that doing perturbations would be very inefficient with respect to modern neural networks. But notice the shift in paradigm. Here he's talking about differentiating with respect to the exogenous inputs. So the input of the system, like the image that the neural network is analyzing. And that's not how we usually use backprop today. We use backprop with respect to the parameters of the network. So when you think about differentiating with respect to the parameters, we're actually saving a lot of compute by not changing each of them individually. And we're only differentiating up to the parameters. So if you look at the parameter at the last layer, you're not differentiating the whole network. You're only differentiating the last layer to know the perturbation value of that parameter. So that's a lot more efficient. That's what he's saying.
Yep. Okay, got it. Thank you. And now he moves to figure 2, which is what we discussed. And he says that the forward pass is taking Z. Z, I think, is the sensitivity, right? It's the change.
The derivative.
Here, it's defined here. It's defined here. Z of t is the sensitivity. So how changing one variable affects another at the output. And he says that you can, forward pass is multiplying by some kind of, I hope everything's okay with the cup.
Yeah, I just dropped it on the table, not on the floor.
Okay, so that's like the forward pass. So if you know its sensitivity at some point, you can just multiply it by this matrix. You call it a matrix or something like that to get to the sensitivity of the output. And if you want to do backward propagation, you can do the inverse or transpose of that matrix. Let's see how he describes it. Computes. Let's see. Here, the key point about those methods is that the forward method is often used when the backwards method would be more appropriate. This can multiply costs. to the point where it becomes infeasible to do what one wants to do. And here it says, for example, it has been long known that economic data, like engineering measurements, are fraught with many errors, and that these errors invalidate conventional estimation methods. Statisticians okay, now he gives examples of like ARIMA. But he says, however, because of the sheer cost of such estimation, it is rarely being done in economics. And so again, he says, doing a lot of forward passes, so calculating from the input to the output is super expensive in large systems. And here, yet in statistical estimation, one only needs a single column of the derivative matrix, meaning, let's say, the error we're trying to calculate, not the whole matrix. Using the backwards method, one can compute all the derivatives indeed in iteration at the cost of only m times n times p. And again, the same motivation. When the output is much lower dimension than the input, you should do backward propagation. It says, likewise, in sensitivity analysis, a user often wants to know the sensitivity of the few key results to all the initial values, or to be sure he knows the largest of the sensitivity coefficients. So he says, only a few columns of the matrix are required. It's wasteful to pay for the whole matrix. Okay, any inputs till now, Mike? You agree with the motivation?
I guess I'm a bit struggling to fully understand this this logic, because I'm trying to compare it to our current neural nets. In our current neural nets, the result is scalar, and the function f dependency, because you have okay, in RNNs and the LSTMs and the recurrent neural nets, you have the same transformation, but our regular neural nets like transformers, you have different transformation in each time, which is layer in neural nets, and your last function is scalar. And I'm trying to somehow project this logic into these modern neural nets, and I'm not sure I'm succeeding in doing it in my brain. And you know, it what you said sounded reasonable. I think I need to dive a little bit in this logic, but maybe I will come to some conclusion towards the end of our episode.
I'd say figure 3 is a good illustration of the kind of cases he's focused on. I mean, there's also figure 5 more later on in the paper. But what do we see here? We see a model which is like a neural net, like a multi-layer perceptron with 2 layers, with the intermediate layer being quite narrow with respect to the input and output layers, and the connections are quite sparse. So most of the inputs, or not most in this example, but not all outputs are connected to all inputs in both layers, right? So I think if you look at the connection, you don't have to calculate all the inputs here. And I'm wondering, I think that if you do that, you can also kind of understand the receptive field of this representation. And then you can also narrow down the forward pass if you understand it. But what he's saying
now I understand
is...
your logic. Now I understand your example of convolutional nets. Because, okay. Now it makes sense.
Okay. I'm glad I managed to say it in a clearer way now. So, well, do you have a good way, Daniel, to explain this diagram to the people listening?
I would say, yeah, you can imagine some kind of multi-layer perceptron I think the main claim here, he's trying to generalize what he said before. And now that you have also like, let's call it hidden layers or something in between, the input and the output, and then you have the chain rule as we are used to. It's called it chain rule, like backward propagation. And the forward pass, he calls it conventional perturbation. So you change, that's what they used to do up to, again, till his work. So to me, this just generalizes what we discussed prior.
Well, let me try.
Even claims the dynamic feedback chain rule has not been published before.
Yeah, that's very important, actually. But I want to try and give kind of a listenable example of how this could work. So let's imagine a company handing out bonuses at the end of the year, right? And let's say, okay, the bonus would be some percentage of the employee's income, of the employee's salary, and that depends on the company's business situation, like how much money the company made that year, which is a fairly common case. So I have all kind of incomes from multiple customers, right? All of that affects company's total income, and then that distributes back to every employee with respect to his salary. That's the size of the bonus he will get. So we have multiple inputs on the first layer, exogenous inputs of what the customers paid. We have one intermediate variable, which is the company's revenue. And then we have many output variables, which is the employees' salaries or bonuses.
Yeah.
Sorry.
And it's linear.
And it's linear in this case. You could put some nonlinear transformations in there, right? But it's linear, but you have, in this case, a very narrow intermediate layer, and the computations all goes through that. So you don't have to, in this case, you don't have to calculate the effect of simulate the forward pass for changing the behavior of every single customer of the company to see how that would affect the bonus, right? So that's kind of the thing he's going for, where you can do something very efficient with differentiation. And it's also a very automatic mechanism that he's talking about, and he's claiming that's the first time this has been published as a feedback mechanism, which is very interesting, and that makes a very strong point towards using that. Some fields were just not able to do this analysis because they were trying to do something so inefficient it didn't work.
Yeah, and he's going to touch upon it in next parts when he talks about like dynamic programming problems. So that's also relates to our previous episodes. I just want to read a short sentence he says here. The methods shown in figure 3 remain efficient even if one uses parallel computers, which are based on many processors operating in parallel rather than one CPU, and they're becoming increasingly common. So that's super cool. He says those methods you can parallelize, which is also amazing insight, because again, even if I understand the math that he's trying to show us, I wouldn't think about parallelizing this. So that's interesting. He had some kind of intuition back then.
By the way, when Liron, when we were talking, it struck me because you can think about some latent models. Think about latent diffusion models, and the first part of latent diffusion models is encoder. You're taking a pixel and you are basically embedding it in some latent large dimensional space. So if you are starting from computing gradients of all your pixels, it will be very, very inefficient. So, and this is the reason that you are doing backpropagation. You are starting from your loss, and then you are coming back to this pixel. Okay, now it totally makes sense. Okay.
Cool. I'm happy to hear that you're on board, Mike. And now he has a part that is generalizing or non-generalizing, talking about the second derivative. So it's not in sensitivity analysis is the first derivative. Now he talks about the second one. and just says that, okay, we can also do forward as we always do, but we also can do backward. So in a sense, it relates to what we call today the Hessian, how I say it properly in English, Hessian,
I guess.
Yeah, of the system. Again, I don't think we should go into this explaining the figure. It's just a 3D cube. But the idea here also with the Hessian, you can do back propagation. And I think that's important part. We can now have like the last part of the episode focusing on it. Where
by the way, regarding the Hessian, Daniel, regarding the Hessian, it reminded me there is a method. Sometimes you need to compute your Hessian for to optimize. We are doing first order optimization, but there are some methods that you can do with at least partially some second order optimization, and there are some methods, I don't remember the name, that you don't compute the Hessian, but you compute Hessian times some vector. So if you have a lot of parameters, say billion parameters, you don't need to compute billion to billion matrix, but you need to compute billion to billion matrix multiplied by some vector. I don't remember how it is called.
So it's like an approximation at the end, some kind of method that approximates the Hessian.
But then I discussed some the ChatGPT, this paper we talked about, and it was pretty sure that it is connected to these methods, but I don't remember name of the method.
That would actually be very interesting in some respects with GANs that are not that popular anymore. But that's actually touching on the issue that made GANs less useful because of the cyclic conversions, because we couldn't compute the Hessians. Yes. So actually, this may be a very interesting research direction even now.
Okay.
Send Leon the paper.
The directional Hessian, yes, please.
Yeah. Cool. So I'll continue to this. In a sense, it's the second part of this paper of PhD, but it connects to what we did. So he talks about application of stochastic optimization over time. And he talks about a method that is GDHP, general dual something. I don't remember where he writes the abbreviation. But the idea here to our listeners, here is tackling the problem of dynamic programming that we covered previously. So you have some kind of Markovian process again, and the next step, t+1, equals to some kind of nonlinear function of the current state, the action that you do, and some noise. And the idea is to maximize this outcome you want to do across all future times. So again, we have a dynamic programming classical problem.
Okay, it's a bit strange notation. Is big U connected to small u?
Yeah, I won't dive into the notation. Okay. Yeah, I'm also not sure. Because there's no definition.
Okay. No,
I'm pretty sure it's not.
Yeah.
Those are different things. Because why would you maximize the exogenous input?
Yeah.
It's not reasonable at all.
And here's important part. He says that economists have proven many theorems about how a large deterministic optimization problem may be decentralized. So as far as I can understand, if you're doing deterministic optimization, you have some value, one value you optimize. Okay, you can decentralize, compute in a sense. But if it's stochastic, what he talks about, then it's a problem. In decentralized, it means like parallel processing. And he says in artificial intelligence, if one does not impose severe constraints on the range of models, like again, if you're trying to do dynamic programming, you need to solve and find and go over all, let's call it combinations and all problems that could be relevant, and that's the curse of dimensionality that Bellman originally talked about, it becomes unfeasible. And then he says, however, numerical analysis have found, even with the much simpler task of maximizing a function of a few variables, that the first derivatives at a minimum are essential to finding a maximum in a reliable, efficient manner.
That's a bit of a weird sentence.
Yeah, I'm not sure what it means exactly. As far as I understood it, is if something is small and well defined, then you can maximize it.
Yeah, but I mean, there are, well, at least now, there are extremum seeking methods that are not reliant on gradients. But I think what he's saying is it will never be as efficient without gradients as you can be with gradients.
Okay. It's basically
Yeah,
like saying if you're doing second order approximation, you can get better results than first order approximation, right?
Well, I think he's saying if you're doing first order approximations, you can get better results than zeroth order approximation.
Yeah, exactly. I just generalize it to the second order.
And
yeah,
here
that's also true.
He talks about how prior research on neurons or perceptrons assumed they are binary, but now in his time, late 70s, they understand it could be continuous, and that in a sense was his motivation to develop the method. And he says the method discussed here, the GDHP, does not address all aspects of stochastic optimization, and the theory needs further development. And so at least he's saying that. And the general approach. So how he's gonna solve this, let's call it dynamic programming problem. He calls it Howard's equation or Howard's book on dynamic programming. I think we reviewed Bellman, and a few years later after Bellman, Howard published a book on dynamic programming, which he referenced here. But again, it's the same concept that we covered. You have the policy, you have a function, you're trying to find the optimal action, etc. And he says in his method, one does not find the exact theoretical solution, which tends to be infeasible with large system. Instead, one assumes that the user or the high-level system has proposed functional forms for the things that we're trying to optimize and all the variables. So what I take from it, again, I didn't understood all of his notation, but he's saying, oh, let's do some kind of parametric estimation. Let's assume that the problem we're trying to solve has some kind of structure. Then we can transform this dynamic programming problem to some kind of optimization problem. When I have like one variable I'm trying to optimize to, and then we can use backpropagation that I talked about prior.
Basically, he assumes the architecture of your model. If we are talking in terms of neural nets, we are assuming architecture of your model, which is how this model depends on the parameter which you are trying to estimate, and loss function. You need basically you need to define two things.
Yeah.
Architecture, loss function. You need some data. He's not talking about data, but I think it is implicitly assumed that he has some data.
Well, if you have a model, you don't need data, right? Here he assumes it just knows the governing equations.
Okay. I see. Okay. He doesn't need.
And here says this method GDHP can be implemented as part of a procedure to optimize the choices of actions over time.
By the way, there's a caveat to that, which humanity will only find that like a few decades after that, right? That I can find what year that was published, but let's touch on it at the end.
He talks about the analogy between this system to the mammalian brain. Again, I don't think it's worth diving into, for sure.
I don't even know what is it, so.
Yeah, it's limbic network, and I don't know, whatever. He's talking about cortico-thalamic system. I don't think it's relevant. It's probably outdated today.
I'll give you the 2-cent version as I understand it, if I understand it correctly. So, in neuroscience, they talk about brain regions, right? So you can say, oh, I have this part here where the neurons talk to each other, but then they are only through like one connection or a narrow connection connected to this other area, then connected to this area. And this actually is connected directly to the eyes, for example. So visual input only goes here. And they talk about the different modules, and then the modules are connected. So that's kind of defining an architecture, as we would call it. So they're saying, like, yeah, you can study an architecture through that. If there's more to it, I didn't really get that deep, but I understood that kind of connection to the architectures we're talking about.
Yeah, and I want to add that important part to what he's talking about is the implementation. And there's, again, a section about it. And the idea there, he says, again, similar to how we do today training. First, he's got the maximization step and minimization. So you're trying to minimize the error and you propagate back. Then you change the variables, and then you get a new error and you calculate it. So he calls it, there's a maximization and minimization steps. And this reminded me of the EM algorithm. That we have also steps that we get something, we freeze it, we change this, and then see how it affects the other thing. And there's like a I don't know how to call it, by-step process of optimization.
It's a iterative process, but I don't get what we are maximizing here. I understand what we are minimizing, but what we are maximizing here.
So you have if we go back, let's say dynamic programming. So you have maximize this J, which I don't remember exactly what it is, but then you have, after you maximize the J, you pick the parameters that maximizes, you need to minimize your loss function.
So it is kind of value function and reinforcement learning?
Yeah.
You are estimating the value function and then you are trying to maximize it? Is it related? It looks like similar, but maybe it is...
No, I think you're right, that there is some kind of first ideas in that direction.
I didn't delve to it, but I understood it differently. Maybe it's my personal background, but I see it as sensitivity analysis is the most naive version of robustness. So saying, okay, if things are not happening exactly the way I thought, I still want to get a good result. So what's a good way to do that? I will say, okay, things will change from where I think they are, and then I still have to get a good result. What do I have to worry about? I only have to worry about the worst change, right? If I do well on the worst case, then I do well on all cases. So I will do sensitivity analysis, like if my system behaves slightly differently than what I expected. Now so the kind of external behavior maximizes my error, and now I have to minimize it with my decisions. And then it will try to maximize it again, and then I will try to minimize it again, right?
So in this interpretation, it is similar to Nash equilibrium and to minimax problem in the game theorem. You are just try to minimize the maximum damage.
So decades later, my advisor will actually work a lot on this formulation of the problem as a game theoretic problem.
Okay. This is actually cool. I think we're gotten some quite substantial depth of this paper, because then I read it. I thought a bit about value function, because this formulation is quite similar, but I've never thought about this minimax. It's really cool, I admit.
So actually, when I think about it, I'm not sure how much after that it was. It was definitely after that year, but that's how I got to know my advisor's work. When I was in my undergrad studies, I did a work on the min-max formulation of the problem.
Interesting. Okay, cool.
And he says also the steps of minimaxing could be carried out in parallel, which is also, you can parallelize this, which is also, again interesting. And just to wrap up, I want to see if there's anything else that is relevant here.
Implementation? Is there anything interesting about this implementation?
No, it just says it's difficult.
I do have the riddle for you at the end, though.
Okay. Implications.
Okay. Yeah, I'm with you, Liron. So, in my opinion, we covered the important parts of the paper. Just to recap, it was like the first backpropagation that is similar to what we do today. And he formalized it. And again, a few ideas in dynamic programming, I think that affected a lot reinforcement learning, because that's the last part that we covered with value function. So again, super cool paper. I agree. It's not so clear because it's some kind of
mess
summary of what he did on his PhD.
But Daniel, the last paragraph are really cool. Implication of the GDHP feasibility. I read it loudly.
Okay.
Loud. This approach makes it possible to develop generalized adaptive artificial intelligence capable of achieving results comparable to what is discussed in science fiction by a rational development of statistics, optimization theory, and numerical analysis in the direction indicated above. The application of psychology and Kahneman's raise issues too complex to permit adequate discussion here.
Yeah.
This is really cool.
It
cool
took
paragraph.
like 40 years from that to find out he was actually correct.
Yeah.
So they predicted 40 years ahead.
Yes, exactly.
Yeah, I agree. I missed that, and super cool that we went over it. How many people actually know this paper? Probably not a lot.
I think many people know this paper, but I don't think many people put some attention on this last paragraph. I nearly missed it, but then my eyes caught science fiction and artificial intelligence in one sentence, and and I started reading it, and but this is the most transparent paragraph in this paper by far, by really far.
Actually, when I was reading it, I was like, wow, this is so cool that he got it back then. And by the time I got home, I forgot it.
Yeah. So what is your riddle?
Oh, okay. So he keeps talking about being able to looking at the connection between time 1 and time capital T, which could be many steps into the future. And then he's like, okay, we can do this sensitivity analysis and we can do the min-max over it and all of that. What is the actual risk of doing that? And can we overcome it? And I think it was only, it took many years later by someone I actually know personally that I was able to find the answer of how to overcome this problem.
I don't understand what you mean by risk. Why there's risk?
Why is that a problem? What is the problem with taking the approach suggested here, specifically for this kind of dynamic system? Let's imagine that, right? I have a nuclear reactor that I have to keep in a desired operating point. Okay. And obviously, if I have a nuclear reactor, I'm not just going to say, well, just, if everything goes well, you should keep working. I'm going to do some sensitivity analysis to say, hey, if things are slightly different from what I planned for, you should still keep working, right?
Yeah.
So say, okay, great. I did a great job here. I used those equations. I solved the min-max problem to make sure I'm not sensitive to anything. What can go wrong?
I can think only about error aggregation. You do stuff iteratively, and if you have some error in computational error, some overflows or underflows, you can just do stuff wrong. But I don't think it is it.
That's actually it. That's great. I'm so happy to be doing a podcast with you. So, one of the things that happened is those things led to an approach called model predictive control. So we have a model, we can predict how things will go forward because we know the system dynamics, and then we want to control it, so make it behave in some way, say keep the nuclear reactor at a set point. They say, great, I can optimize T steps ahead, but nothing ends within T steps. The nuclear reactor has to keep going for a very long time.
Yeah.
Right? We don't say, oh, you know what, if it's running for over a year, I don't worry about it. So if error actually propagates, or if anything like can deviate over a very long time that we cannot calculate, then we will have a problem. And basically the whole field of model predictive control had like no solution to that. I said, we'll optimize to some point in the future and we'll hope that's enough. And obviously no one would rely on it that way, right? No one will say, okay, you know what, if the airplane is, balanced in the air based on this method, I'm happy, let me take that flight. No, people say, I'm not taking that flight. So, and the person that actually solved that, his name is Frank Algover. Algover. He's a German professor from Stuttgart that I knew during my postdoc. And he just had like the most weird, but it's a brilliant idea on how to actually solve that problem. Of course, that's the most basic way to solve it because there were no solutions. So Mike, or Daniel, do you want to try and guess how did he actually solve it? That error can keep accumulating over a very long time.
I think you need to compute the real value of this function once, every minute, every hour, every number of iteration, and it is very similar to training LLMs with reinforcement learning, all PPO. You are doing offline reinforcement learning, policy of reinforcement learning, because you are sampling from the old policy, and then it is basically this. But from time to time you need to update your model. And how do you update your model? You evaluate it.
Well, I'm not sure how to really consolidate what you said with what Frank said.
Okay. Reduce dimensionality.
Okay.
Daniel, do you want to try, or do you want me to tell?
No, it's intuition, so it's not based on math. I would say you need to have some kind of way to erase it. I don't know.
Critique?
How?
No.
To evaluate like similar to let's say you have drift in, I don't know, in your GPS or whatever over time, right? So you do some kind of calibration, but you don't have the ground truth in your case, so I don't know how to do calibration.
Well, brilliant, great. I'm in the right place in this podcast. So yes, that's exactly what Algover did. He said, well, look, I have the set point of the nuclear reactor or the airplane or whatever it is, right? This is where I want to bring it. So when I'm planning T steps ahead, let me make sure I'm bringing it exactly to the set point. And if I end up at the set point within T time steps, I'm good. So I know that if I'm at a set point, I'm good. I know that I can get there within T time steps. So I've actually proven everything I have to prove.
Okay, interesting. Okay, it is simpler than I thought. Okay.
Yes, like I said, that's the most simple approach. You can take two other approaches as well. One of them is having a Q function that guarantees, well, we call that in control a Lyapunov function, but that's roughly analogous to a Q function. We say, well, if I'm in this Q value, if I can compute the Q value from here on, then I'm actually happy, right? I know the Q from here, so I can just rely on that, which is a more advanced version. And also, you can also do contraction. So you can say, well, I'm in some area in space, and I know that if I start in this area, I will end up in a smaller version, epsilon smaller version of that area on all dimensions. So I get a contraction property.
Yeah. Some kind of stability, right?
Exactly.
Yeah.
And it's actually called Lyapunov stability. Or asymptotic
I
stability.
love this stuff back in 2004 in a course which was called asymptotic methods of solution of partial differential equations, and
oh wow,
it was hell of a course. It was one of the most difficult courses I ever
sounds
had.
hardcore.
Yeah.
Cool. So I enjoyed the episode. Although we had doubts, we will be able to decipher it, but I had fun. So thank you very much.
Daniel, you can enjoy, even you don't understand the paper you are discussing almost in an hour. We are talking almost a whole hour, and it was really cool. Although we're not, I don't feel I understand it. I understand it in 16%.
Okay, that's why we have upcoming episodes about. We're probably gonna cover now Hinton's papers. So.
Yes.
I have no idea
how
well I understood it, but I'm happy we made this episode.
Yeah. But
yeah,
today I know more than I knew 1 hour before. And it is cool because, you need to constantly learn.
Amen. I like this mindset. So thanks a lot, Mike and Liron, and thank you to the listeners.
Thank you, Daniel.
We'll see you on the next episode.
See you.
Bye.
Bye.